All right, there we go. Okay. So let's see. I think for introductions, what we should do is just a real quick, name, affiliation, and what your interest is in Corundum. If it's just a personal interest thing, or are you, using it for research, or using it for a commercial product or something along those lines. So I'll go ahead and go first. My name is Alex Francich. I'm a postdoctoral researcher at UC San Diego. I built Corundum over the past couple of years. It was my, PhD thesis project, and currently we're using it for, various optical networking research projects. And that about rounds it out for me. So let's see, who wants to go next? I can just go down the list here if we don't have volunteers. All right, let's see. I have Alberto next on my list in Zoom. So
my name is Albertlern. I'm a senior researcher at the University of Freiburg in Switzerland. Our interest in Corundum is we are designing network cards that can offload certain tasks off of database applications. And we want to do that through an RDMA framework. So, and this is, our interest is purely research.
Okay. And I guess next on Zoom's list here is Andre.
Hey, so my name is Andre. I'm from the University of Fribourg. I work with Alberto. So yeah, basically what he said, right? So we're trying to use Corundum with RDMA in the context of database systems.
Okay, the next on my list is, I'm going to butcher this probably, Joachim?
Almost, Joachim.
Okay.
From Germany.
Okay.
So my name is Joachim. I'm working for Missing Link Electronics, and a few seconds ago I did see Ulrich, my colleague, and I guess you know Ulrich already. So we try to, we're looking at Corundum, and I have the question if we can use it for commercial product.
All right, sounds good. Hopefully we can make it work for you guys. Let's see.
We'll see.
So who's next on my list here? Joseph, Tony?
Hi, I'm Joseph Tony. I am an undergraduate researcher at the University of North Texas. I'm currently using Corundum to offload packet filtering using Vitis AI, and I'm going to try to port extra support to the ADM 8v3 and hopefully to the Mellanox Innova 2 NICs.
Well, it sounds like a fun project. You said you're an undergraduate.
Yeah, so I'm a non-traditional student, so I've been doing data center work for a long time, and I just went back to get a degree, and I've been trying to learn FPGAs as my research.
Well, very cool. So presumably you have a faculty advisor or something along those lines then?
Yeah, I do. They do like a directed study kind of program.
Okay. Well, we'll have to see if you can get some boards through the Xilinx University program then.
Yeah, that'd be cool. I mean, I also just have some boards I picked up off eBay because they were super cheap.
Likewise. Maybe too many for me. Anyway, that's really cool. Well, let's move on then. Who else do we have? Matthias? I think I'm pronouncing that correctly. Oh, I'm not hearing anything.
Can you hear me now?
Oh, yeah, I can hear you.
Okay, yeah, I'm a PhD student from TU Darmstadt in Germany, and I'm just today here to get a look on your project, what you were doing. And last week I've met Alberto, and he really recommended you and your group here, what you are doing with the FPGA stuff.
All right, nice. Got some word of mouth advertising going. Okay.
Yeah.
So you're joined twice to the Zoom. It looks like with two different names. No.
I'm only once here.
Oh.
What do you mean?
Oh, never mind. Okay, sorry. I saw somebody else unmute, so I thought. Never mind. Okay. All right. I just wanted to make sure I didn't call on somebody twice accidentally. Okay. Cool. That's really. So are you working with Alberto then, or?
No. We had just some meeting.
Okay.
And I'm currently working on my own project, but the next project will be going in the direction of RDMA and some programmable switches and FPGAs maybe.
Okay. All right. Well, very cool. All right. So who's next on the Zoom list here? Kukarov. You want to introduce yourself?
Hello, can you hear me?
Yes, we can hear you.
Hello, I am Shkuro and I work for a company called Bulltech. It's mainly producing trading products, HFT products, but we are planning in the future maybe we'll design UPF and DPI 5G products. So I personally, I'm interested in this project. I am following this project to learn more and to have friends, to make friends from other guys who are working with FPGAs and this kind of things. It would be nice. So I'm following this project.
All right. Well, it's good to hear. I'm also hoping to make some friends and build a community through this. So seems to be
Yes.
moving a little bit in that direction. So that's always a good thing.
Yeah, sure.
All right. Let's see who's next in the Zoom order here. Let's see, Thomas.
Hi, I'm Thomas Michalak. I'm an engineering manager at Micro. It's a service company based in Sweden and Poland. Well, we are interested in your project mostly because we are doing some R&D around computation and storage devices. We use part of your project for the PCI communication, PCI Express bridge communication. And it's looking good so far. So we are at least looking at how it's progressing, and possibly at some point could help you out also implementing some stuff. But we already use part of your project and around our R&D work, so we know it's working. And these we are mostly working on with FPGAs on UltraScale Plus devices.
All right. Well, that's really good to hear. It's not completely full of bugs. All right.
No, it does not. And
so you said you're using mainly the PCI Express interface components. So you're not using the Corundum design as a whole, but more just the PCI Express interface and the DMA components.
Yeah. At this point, well, we used some of the blocks that were developed like several months ago, I guess. And at this point, we are just looking at how it's progressing. And but actually, yeah, we are interested at this point only in part of the communication part.
Okay. Well, that's a pretty important part of the whole design. So I've definitely been spending a lot of time making that part work well, because if that part doesn't work, then you can't send and receive packets at line rate, So
Yeah,
it's
exactly.
good you guys have been able to make use of that. All right.
Yeah.
Well, let's see who else is in my Zoom list here. Ulrich. Not getting any audio, unfortunately.
double mute myself.
there we
Yes,
go.
I did. The good double mute. So once again, hi everybody. Hi Alex. I'm, as Joachim already said, I'm also with Missing Link Electronics. We are looking into the project. So I myself looked into the project for a couple of months now. I was just having personal interest in it, but now we are seeing the option to base a product on it, and we are investigating various portions of it. And one is the DMA part. So that's why also Joachim is here today. And yeah, we are also happy to contribute additional portions that we develop for the infrastructure, for example, in the future. So happy to work with you guys.
All right. Well, that sounds great. Let's absolutely make sure to keep a channel open, for anybody that's potentially going to be making some modifications or, some contributions. The more collaborative we can keep the, the design process, the better, right? But that's why we have these meetings here. So there's a nice opportunity to coordinate this sort of thing. All right. So let's see. I guess what I'll do next is pull up the slides that I put together on the DMA subsystem in Corundum. And then we can go over that. And then after that, we'll, I guess, see if anybody has anything that they want to discuss. Let's see here. Okay, I need to get that going, and then well, it's, I suppose, a good thing that a number of people currently connected are interested in the DMA subsystem and PCI Express, because that's what I prepared some slides on for today. All right, so what I'm going to talk about are a couple of things, very brief kind of introduction to PCI Express, so the rest of the slides will make sense, and then just a very brief kind of development history of the DMA subsystem in Corundum, because I didn't, the current version is not something that, didn't come together immediately. It went through a couple of revisions to get to where it is now. And then at the end, I'll just have kind of a pretty high level overview of how the subsystem works in Corundum. All right, so first, simple primer on PCI Express. So PCI Express is based on an older standard. Well, it's related to an older standard called PCI. PCI stands for Peripheral Component Interconnect. It's a shared bus that can connect a CPU to associated peripherals, and it supports memory and I/O operations between the CPU and the peripherals. And one of the advantages of PCI is any particular device can assume the master role and perform operations. So this allows the devices to talk to each other without the involvement of the CPU. And it also allows for DMA. So a device can directly access host memory, again, without the involvement of the CPU. And PCI has a configuration space that's used for enumeration and control, which is rather useful. This is in contrast to something like most of the existing ARM SoCs, where you don't really have any method for determining what peripherals are present besides a device tree that just lists it all out. So in PCI Express, you can poke at a device through the configuration space. You can figure out what it is, what kind of resources it needs, and what driver to load. PCI Express replaces PCI, but it is backwards compatible from a software perspective. So the hierarchy and the way addresses are assigned is somewhat similar. It uses the same configuration space method. It performs the same kind of operations in terms of memory and I/O operations. But instead of using a shared bus, it uses packet switch point-to-point links, right? We're literally building a network here for PCI Express. and it has a hierarchical structure with, the root complex at the core, and then, layers of switches and devices that are connected to the root. And I also mentioned that PCI Express is a hardware protocol, much more so than something like Ethernet, where you have a lot of, software visibility into what's going on and a lot of software-based tools. In PCI Express, everything is implemented in hardware, so you have, relatively limited visibility from software. The flip side is this does mean that since everything is handled by hardware, you can get, pretty high performance without involving the CPU. All right, so a little bit of terminology here. There's a couple of components in a PCI Express system. The first one is kind of the root complex, and this sits at the root of the hierarchy, hence the name. It contains a CPU and the memory, and potentially some root complex integrated endpoints. And then most of all right, so the term function is any addressable entity in configuration spaces, and it has a PCIe ID. And there's a couple different kinds of functions. Switch ports are functions, and then endpoints are functions. And the endpoint is kind of a leaf device in the PCI Express hierarchy. So, any kind of PCI Express add-in card would implement, one or more PCI Express functions. And a function or an endpoint can act as a requester or completer of a PCI Express transaction. So you can, the endpoint can, generate read and write operations, or it can also accept and, terminate read and write operations. All right, so PCI Express, similar to Ethernet, is built in several layers. You have the transaction layer, which is kind of the highest layer. This one is what actually implements the various operations. So memory, configuration, IO, reads and writes, completion packets, message packets. The transaction layer uses credit-based flow control to make sure that, packets get transferred properly and you don't have buffer overruns and things like that. The data link layer sits below the transaction layer, and this ensures the reliable delivery of transaction layer packets. So this has an acknowledgement protocol and retransmit scheme. So if a packet gets corrupted, then it will be retransmitted. Data link layer also conveys the sequence numbers and flow control information. Below that is the physical layer, and this implements the actual electrical signaling. It has the SEER-Ds, clock data recovery, equalization, deskew, line coding. All that stuff exists at the physical layer. So for the rest of this talk, I'm only going to be touching on the transaction layer. Usually when you have like a PCI Express IP core on an FPGA or on an ASIC, you're going to be working at, the transaction layer, or, potentially talking to a hard DMA engine. You won't be working with anything below that. All right, so at the transaction layer, everything takes place in the form of transaction layer packets. So these packets, or TLPs, describe various operations. So memory, config, IO, reads and writes, completions that can carry data in response to, memory reads, and then messages, which can be used for various purposes. You might think messages are used for message signal interrupts, but actually MSI uses memory writes, not messages, but messages are used for a few other things. PCI Express is a D-word oriented protocol. So that means that most of the various fields inside of the packets are, in terms of the number of D words, not the number of bytes. The sizes of the packets are all, integer numbers of D words, things like that. There are a couple of size limits associated with TLPs. There's a maximum payload size and a maximum read request size. Both of these are set in the configuration space, so software can actually change these values, usually not so much at runtime, but at boot time. So different systems will sometimes configure devices with different max payload size, max read request size, depending on the system configuration and the performance requirements and whatnot. Max payload size on older CPUs seems to usually be set to the minimum 32 D words or 128 bytes. Relatively newer systems seem to set it to around 256. And the only machines that I've seen set it to 512 are the AMD EPYC Zen 2. Possibly there are other systems that set it harder, that set it higher. The max read request size is usually set to 512 bytes on pretty much every system that I've seen. On some of them, BIOS will kick it up to 4096. The PCI Express TLPs, generally they can be routed either by address. So if you have a, if you have a memory operation that's operating on a particular address, then you can route it by the address, or they're routed by the PCIe ID. So this is generally used for completions, and configuration requests. Messages can be routed by either, depending on what kind of message. All right, so for today we're mainly looking at DMA. So how do memory reads and writes work? How are those propagated across the bus? All right, so memory reads and writes use a TLP that looks like this. Well, I have two different formats here, but they're basically the same thing. The only difference is the size of the target address. So the important fields here are the length, right? How many D words is this operation going to be? How big is the payload in the packet? And then for writes, at least, you have the first and last D word byte enables, because since everything is done in D words, if you want to do like an unaligned operation, or you want to do an operation of less than one D word, you want to disable the bytes that you're not trying to touch. So there's the first and last D word byte enables. Then there's the requester ID. This is used to route the completion back to whoever issued the request in the first place. And then there's a tag. This is used to associate completions with the original request. And this is important because you can actually issue multiple read requests at the same time to the same device. So the tag you use to differentiate which completion corresponded to which request. And then there's a target address, and finally the payload data, which follows the TLP header. And the payload data is only used for the write request, and that's basically the difference between read request and write request, is whether or not the TLP has a payload. All right, so that's the request TLP that you send. The memory write TLP that's a posted request. So you just send the TLP and that's it. For memory reads, that's a non-posted request. So you send the read request, and then sometime later you will get responses back in the form of completions. All right, so completions are used to either carry the read response data or the response to a configuration operation or IO operation, or they can be used to indicate some sort of a problem. So for a completion TLP, you have the length in D words, same as in, say, a read request. Then you have the completer ID. This is to associate the completion with the request. Then there's a completion status that's used for reporting errors. So if there was like a routing error in terms of a request that was issued, then one of the switch ports could respond with an unsupported request completion. Or if it arrives at an endpoint and it's for something wrong with the request, then that can be propagated back. Following that, there's a byte count remaining field. This is used to indicate, it's used to detect when you're looking at the last completion in a sequence from the same read request. And it's also used to indicate, the last valid data byte in that completion. Presumably if you issue a read, you know what bytes to expect in the response, but you can also determine that by looking at the byte count remaining field in the completion. Then there's also the requester ID, and that's primarily used to route the completion back to whoever issued the original request. And then there's a tag, right? This is returned in the completion. Again, that's used to associate the completion with the original request. And then finally, there's also a lower address field, primarily uses to figure out, the first byte, the first valid byte in the response data in the completion. It only gives you 7 bits, I think. So it's not the full address, but it's enough of it to make sure you're looking at the right thing. All right, so PCI Express, like I said, is it's a hardware protocol. It's implemented entirely in hardware. Software has no visibility or control over TLPs. So from the software perspective, you're not going to be piecing together TLPs like you piece together an Ethernet packet. You're simply going to perform memory reads and memory writes, using load and store instructions on the CPU to, perform these operations. Now, from the other end, from the accelerator or an FPGA or add-in card, then you're going to be more directly interacting with the PCI Express. So because software has no visibility over this, then there's no like Wireshark or TCP dump or whatever tools for PCI Express, at least not without extra hardware. So if you have like a PCI Express protocol analyzer, then that basically does what Wireshark does, but you have to have this extra box that gets plugged in, and yeah. It works when you need it, but they're bulky and expensive. It's not as nice as in the software world, where for Ethernet you can just fire up Wireshark and capture all the traffic going out your NIC and you're good to go. All right, so inbound requests to the CPU are handled by hardware in the memory controller, so software never sees those. And for outbound requests, you can generate those exactly like you would accessing memory. So this is where memory mapped IO is kind of the term for what happens when you perform memory operations and they go to an IO device instead of accessing memory. So a little bit of terminology. All right, so how do you write to memory using PCI Express? It's relatively simple. You issue memory write TLPs, but there are a few rules, right? So the data has to be DWORD aligned at host memory. So you may have to pad things and shift things appropriately so it all lines up. And you may need to split an operation against or across several memory write TLPs. So you have to look at the max payload size setting and make sure that you're not generating any TLPs larger than that. And then you can't issue requests across a 4K address boundary. So this happens to coincide with the page boundary that most operating systems use for managing memory. But yeah, you can't cross that. So if you want to transfer something across the 4K boundary, you have to split the operation on that boundary. And I recommend checking for sufficient flow control credits to prevent head-of-line blocking, which can be an issue with some PCI Express IP cores. They will, block the port for accepting more TLPs if they don't have enough credits. But the problem is there's several different types of credits. So what you can do is issue a bunch of memory reads and then block the interface. And then you can't issue any writes until some of those credits get freed up. So I'm not going to talk at all about flow control in this presentation, but that's generally a good idea to make sure that you have enough flow control credits before you hand something off to the PCI Express hard IP core for transmit. All right, so for writing to memory, that's relatively simple. You just basically generate these TLPs according to the rules, you send them, and the write takes place when those TLPs arrive. All right, what about reading? All right, reading is a little bit more complicated. What you have to do is issue memory read TLPs. And again, because everything is DWORD aligned, you may need to offset the read appropriately by a couple of bytes so that the alignment is correct. And you may also need to split the transfer across multiple TLPs. In this case, you have to look at the max read request size setting instead of the max payload size setting. And again, you also can't cross 4K boundaries. So you do all that and you can issue your TLPs. The other thing that you need to do is assign a tag from a tag pool, basically. So the default tag pool is 32 tags per PCI Express function, and that can be extended to 256 tags when the extended tag bit is set in the PCI Express configuration space. So you can't reuse a tag until all of the completions have been received for the previous operation using that tag. So this kind of sets an upper bound on the amount of outstanding read data you can have at any given time, right? Because you have a certain number of tags, and then you have a certain size for each one of those requests. So for some applications, this could be a problem, and this can definitely be a problem if you're issuing a lot of small reads. And then once you've issued all the read requests, then you have to deal with the completions that come back and extract the data and handle it appropriately. So issuing the TLPs is not too bad, basically the same as writes, but dealing with the completions is a little bit more complicated. And this is because the completions can get reordered, right? So each memory, well, the completion can get reordered, and each memory read request that you issue can actually result in multiple completions. So, like I said, there's two different size components to the TLPs. There's the maximum read request size and the maximum payload size. Usually the read request size is going to be larger than the maximum payload size. So that means you can issue a read request for, say, 512 bytes, but the max payload size is only 256. So you're going to expect at least 2 completions for that read request, potentially 3, potentially even more. The root complex will split read operations on 128 byte boundaries. So if you're going to split, sequence of requests, it might actually make sense to split it on a 128 byte boundary. So you have less TLPs or less completions coming back, which means, less header data needs to be transferred, which improves performance a little bit. Completions for the same request have to arrive in order. So if you issue a completion for a particular read request, you're going to get the completions, or if you issue a read request that has multiple completions, you're going to get those completions back in order. But completions for different requests have no ordering requirements. So they can be interleaved and reordered pretty much endlessly. And, from the standpoint of the DMA engine, you have to unwind all of that. All right, so just as a real quick example, let's say you issue 2 read requests, each read request resulting in 2 completions. Well, it's possible you could get the completions back in order like that, right? You issue read request A and B, you get completion A1, A2, B1, B2. That's possible. But that's certainly not the only option, right? Maybe that happens, right? Maybe you get A1, B1, and then A2, B2, right? That could happen. Or maybe you get all of the B completions before you see the last completion for A. Or maybe you get the inverse of that and you see the first B packet before you see anything from A. Or maybe you see the entire second request complete before the first one completes. All of these are perfectly valid in terms of the PCI Express ordering requirements. So the DMA engine in the receive direction has to be able to deal with all of this. All right, so moving on to how things work in Corundum. So the DMA subsystem has gone through 2 major revisions, but there was one kind of on the drawing board before that. So the first idea that I had is, well, we're just dealing with Ethernet packets here. Couldn't we just do everything with, AXI stream? Ethernet is packets, PCIe is packets. That should be easy, right? Well, like I just said, with all this ordering, this doesn't really work. No ordering is enforced between completions with different tags. So either you can only issue 1 read request at a time, which results in terrible performance, or you have to deal with all of this reordering. So you need some sort of a scratchpad RAM basically to unwind it. As the completions are coming back, you write them out into the scratchpad RAM, and then, once you have all of the pieces in the right order, then you can read the data out of the scratchpad RAM. Additionally, for streaming interfaces, you have potentially headline blocking problems. So if you've, partially transferred something through a streaming interface, that streaming interface is kind of, locked down until you've completed that operation. And that can potentially be, a performance problem, especially if you have multiple, Ethernet ports. It doesn't make sense to, have a streaming DMA engine trying to send data to multiple ports if you're going to have, traffic from one port, jamming everything up. You need to do some additional work to make that work. So it seems like all this considered, it would make more sense to start with a, memory mapped internal interface instead of trying to do everything streaming. If you want to do everything streaming, you'd basically have to do this internal to the PCIe DMA engine anyway. So it might make sense just to separate it out. All right, so first actual implementation I did was, let's just use AXI. Xilinx uses AXI for everything. Might as well start there. Xilinx uses it, it's probably good, right? The idea at the PCI Express DMA level is relatively simple. The DMA engine is basically doing protocol conversion, right? It'll issue a PCI Express read request. It will get the completions back. It will take those completions and it will convert them to AXI write operations. Or in the other direction, you will issue AXI read operations, and then the PCI Express DMA engine will accept the read completion data from the AXI interconnect, AXI infrastructure. It'll convert that to PCI Express write TLPs and send those out on the wire. And then we'll use, AXI RAMs for Scratchpad RAM, and then an AXI to AXI stream DMA engine to interface with the Ethernet ports. So we put all that together. I wrote a whole AXI library and, my own AXI interconnect components, yada, yada, yada. It worked, but the performance was not great. And there were a couple of reasons for this that I figured out pretty quickly. The first one is ordering constraints. It's hard enough dealing with ordering on the PCIe side. I don't want to deal with that on the AXI side as well. So the only solution to that is you use just a single tag for all of the reads, so you don't have any interleaving. But the problem is that the interconnect doesn't allow accesses to different devices with the same tag, so such that it can preserve the ordering within that same tag. And that results in basically not being able to use any of the pipeline delays to improve throughput. So the result is terrible throughput. Additionally, there's throughput reduction due to alignment, and this is a more difficult problem to solve. All right, so performance problems due to alignment. The DMA engine has to realign the data during transfers. So like I mentioned before, the TLP payload data is D-word aligned in the host address space, but inside the FPGA, the data is aligned based on the internal addressing. And these are almost never going to coincide. And you can compute probabilities and whatnot, but the thing is the addresses used here are not random, at least in terms of the least significant bits. And it turns out that basically every single read, every single write, every single transfer that you make has to be shifted to get things aligned. Maybe not every single one, but vast majority of them need to be shifted. And shifting the data requires additional transfer or access cycles. So for example, if you received, 4 data bytes in 4 lanes, right? 4 byte lanes could be like a streaming interface. If I need to shift this first byte into the second byte lane here, well, if I do that, then what do I do with this last one? It gets shifted off the end. So you have to transfer that in a subsequent transfer cycle, right? So I either need to perform, 2 reads against the RAM here, or I need to use 2 clock cycles to transfer this over AXI stream, or over AXI as well for the packet payload data. That's a whole additional transfer cycle. So this reduces the throughput, and it's a larger effect for smaller packets, right? And PCI Express packets are relatively small, right? 128, 256 bytes. That's very small compared to Ethernet frames. So if you transfer a 1500 byte Ethernet frame, that's like 6 TLPs right there. Maximum size TLPs, and if you need to pay this for every TLP, right, that's an additional 6 transfer cycles right there. That eats into the throughput, and it's also a problem for wider interfaces, right? Because wider interface, you're going to transfer that TLP in fewer clock cycles, right? It might only take 4 clock cycles to transfer a 256 byte TLP, but if I have to pay a whole additional clock cycle just for alignment, for every TLP, and have this gap and all these unused byte lanes, that becomes a huge detriment to performance. So the question is, what can you do about that? How do you mitigate this? So the first idea that I had is, okay, what if you just use a wider interface, right? PCI Express, maybe we have a 256-bit interface. What if we use a 512-bit memory interface to our Scratchpad RAM? Well, it's a start, but you still have wraparound, right? If you go to the end, you can shift a lot further, but you still have a wraparound. So this doesn't solve anything. But what if we use 2 interfaces, right? What if we have 2 separate memory interfaces and we stripe the data across these interfaces? Then what we can do is we can always access that adjacent memory location. And you can think of this as we have an even interface and we have an odd interface. So, if we're counting up the addresses here, this would be address 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, so on and so forth. So if I shift this all the way down here, right, if I started out on like, this is address 6, 7, 8, 9, right? I can make that work in the same transfer cycle, in the same clock cycle, without having to spill this into, subsequent clock cycles. And with this setup, using two interfaces, we can access data at any alignment in a single clock cycle. So this is perfect for DMA, and we can do this for both read and for write. So this ends up being perfect for DMA because you can get 100% throughput. All right, so this was kind of the idea that drove the development of the segmented interface that's used in the current incarnation of the DMA subsystem in Corundum. We have a double width internal interface that's split into multiple segments, and we can access data on this internal interface at any alignment with no extra transfer cycles. The interconnect preserves ordering, so unlike AXI, we don't have ID fields. So it operates similar to AXI Lite, where just the order you issue the reads is the order you get the read data back. And as a result, the DMA engine doesn't have to deal with any sort of reordering on the internal interface, so you can get good performance. And then we coupled this with some additional ideas to come up with the modular DMA infrastructure that's used by the current version of Corundum. So the DMA engine is split between interface and client modules. So the DMA interface module is facing the host. So the DMA interface would be connected over PCIe or potentially AXI if you're running on some sort of an SoC. On the other side, you have the DMA clients. These have the internal ports, right? So AXI stream, AXI master, AXI slave, or if you wanted to make them for Avalon or whatever protocol you want, you can make your own DMA client that speaks that protocol. As a result, you can mix and match various clients, right? You're not limited to having one big honking PCIe DMA IP that gives you one AXI interface. If you need several smaller AXI interfaces, or you want to run these in different clock domains, or you want some AXI and some AXI stream, you can do that. You can mix and match. And the clients are connected to the interface module with parallel simple dual port RAMs. And because we're using these parallel simple dual port RAMs, you could also make these dual clock, and then you can run the DMA client synchronous with logic that could be running faster or slower than the PCI Express clock. So it makes everything really, really, really flexible. All right, a couple more notes about this setup. The segmented internal interface, like I said, is based on AXI Lite. You get same cycle access to adjacent locations. We use a separate select signal instead of address decoding. So we actually have, if you look at the interface, we have a select signal and we have an address signal. So the address is used to, address into the RAM. The select signal is used to select, which RAM you're talking to. And this makes it a lot easier to parameterize the interconnect components. Now, the other thing about the setup is that the interconnect preserves the ordering. So we actually have some FIFOs in the interconnect components that keep track of, what ports have issued requests, and that's used to determine, what order the responses are going to be passed back through. The parameterizable interconnect components means that you can very easily change the number of ports that you're hanging off of a DMA interface module. So these handle all the select signals automatically. They manage not only the request and completion information going to the DMA interface module, they also manage the segmented interface connections going to the DMA RAMs. And they're all set up to do the right thing without needing a bunch of additional work. If you have 2 ports on a MUX module, they will automatically compute the select signals in the request and modify that so that when the DMA interface actually carries out the operation, it will go back and come out the correct port and hit the correct RAM. All right, and another thing about this setup is it's potentially very useful for FPGA acceleration shells. So if you've ever worked with something like the Xilinx Alveo boards, for example, they have a DMA engine that's accessible from, or that's accessible inside the reconfigurable region. But the only kind of annoyance is that you're limited to, whatever interface that the external DMA engine provides. So maybe it's just a big honking AXI interface, maybe it's several streaming interfaces. That decision has been made by whoever made the shell. But with this modular DMA setup, what you can do is just pass the segmented interface through to the reconfigurable region, and then inside of your reconfigurable logic, you can place the simple dual port RAMs of whatever size that you need, whatever MUX modules that you need, and whatever DMA client modules that you need for your application. So if you want to run a DMA interface, or if you want to run, say, an AXI interface at a lower clock speed and then have a streaming interface that's feeding your data path at a much higher clock speed, but maybe narrower width or something, you can do that. And it's relatively efficient in terms of logic resources. So yeah, that's about all I have in terms of how the DMA interface in Corundum works. Maybe this will help you understand how Corundum is put together a little bit better. All right. Does anybody have any questions about that? No? All right, it all makes perfect sense.
So as Ulrich pointed out, and I forgot to say at the beginning, we are currently looking right at that DMA interface between the MQNIC core and potentially then connecting it to an AXI instead of PCIe.
Right. Yeah, so I've actually been working on a DMA interface module for AXI. I just have not had a chance to test it on an FPGA yet, make sure it works. So it works in simulation, but yeah, I haven't tested it in hardware yet. But I'm hoping to do that relatively soon, and then I'll get that up in the repo. So you guys might be able to make use of that.
Yeah, that sounds great. Yes. Because we looked at the interface, and to a certain extent, it becomes clear what there needs to go on. But to be honest, it's we are not really through with it, and I guess some question we have are answered by your presentation now, so that's very good. But one thing I wonder about is the algorithm to stripe those data bytes to those segmented RAM interface. That currently it still seems like magic, to be honest, to me.
I mean, it's the code is not maybe particularly easy to follow because it has to be written in a it's written in a way that works well for timing performance, but is not necessarily easy to read. The idea is that you're basically striping the addresses. So if you think of the full address that you're getting, that you're issuing for the kind of the destination of a read operation internally, the low order bits select kind of the byte lane in one segment, and then if you go up, the next few bits then determine which segment, and then the rest drives the address for that segment, if that makes sense. That's all that's going on, and the code to determine which byte enables to set and whatnot is a little bit more complicated than that because it it needs to be done for timing performance reasons. And to be honest, that particular piece of functionality is one of the biggest head scratchers that I had when I was working on this in the first place. I'm like, I had no idea if that was going to close timing or not, and it took some work, but it does seem to work reasonably well even on slower devices. So yeah, in general, there really isn't an algorithm for picking which segment to use. It's just based on the address. And then there's a little bit of logic for wraparound, where you have to look at the +1 basically.
Yeah, the +1 thing. Yeah, we saw that.
Maybe there's a better way to write that will work a little bit better performance-wise, but that's the best that I could come up with.
So your simulated code is using exactly that interface and connecting to AXI instead of PCI. It's not at some other point.
Yeah, actually, let me see here. Do I have that module sitting around that I could just pull up? I think I do. Let's see. Oh, not that one. All right, one moment. All right, come on, Zoom. Okay. Share the desktop. Okay, there we go. Yeah, so this is the AXI DMA interface module. I'm not sure if you guys can see that. It's probably a little small. But yeah, so if you look at the ports that are set up here, we have an AXI master interface. Then we have the descriptor connections here that are used for controlling the DMA transfers, and then we have the segmented RAM interface at the bottom. So that's the idea. So this will basically just be a direct drop-in replacement for the PCI Express version. And the same kind of thing. We have a write version and a read version that implement just that portion of it. Now, I think one thing about this code right now is that it doesn't handle reordering as completely as the PCI Express one. So like with the PCI Express version, you can basically reorder things endlessly, and it'll figure things out. I think a lot less reordering happens in a lot of AXI based systems. I mean, if you're touching different peripherals, that's going to be a different story. But if you're just going to and from RAM, I think you're basically going to be getting things back in basically the same order. I'm not sure if you guys have much insight into that, if you guys are working with some of the Xilinx SoCs or something else. That would be good to know. I mean, if things get reordered, it'll still work, but it won't recycle the tags as efficiently. It only releases the tags in order, basically, versus in the PCI Express one, it stores the tags in a FIFO. So if they come back in whatever order, it'll just put them back in the FIFO, and then it could reuse them immediately.
I also have one question about 4K boundary.
Sure.
So if the page size is different, should we check for different boundary? I mean,
well, okay. So if your page size is smaller than 4K, I don't know how you handle that. But PCI Express only supports 4K boundaries. That's coded into the spec. It happens to align with the standard 4K page size used on a lot of systems. If you use a page size larger than 4K, as long as there's a multiple of 4K, then you're fine. If it isn't the multiple of 4K, then I think you need some help.
so I mean, if the page size is multiple of 4K, but it's huge, so can we change the codes like to check only for example, if it's
no
32K.
So for PCI Express, you're not allowed to issue request crossing 4K boundaries. It doesn't matter what the page size is set to in the memory controller.
I mean, not the request size, but memory space. I mean, for example, I checked the DMA code, your DMA code, and I saw that if there are two back-to-back packets, and one is, for example, 3 kilobytes, and the next one is also 3 kilobytes, Then if one goes to memory, and the second should go in two parts, one smaller and one bigger, one 1 kilobyte and one 2 kilobyte. So there is performance decrease, right? In this case.
I mean, yeah, but there's not much you can do about that because PCI Express spec says you cannot cross 4K boundaries with read or write requests.
Okay.
So doesn't matter what the page size is. It, like I said, it happens to coincide with the page size on a lot of systems, and it's probably done partially for that reason, so that the memory management unit doesn't have to, deal with PCI Express operations that, somehow cross two different pages. But yeah, because it's specified at 4K in the spec, you can't just change that because all the devices in the system outside of the FPGA that you're working with are potentially going to be assuming that you don't have things crossing 4K boundaries. So either you're going to get, so one possibility is that it works. It's possible, but I wouldn't rely on it. Possibility number two is that something unexpected happens, right? System crash or something else, or reads the wrong data or something. Not sure about that. Possibility number three is that it's checked somewhere and reported as an error, handles a malformed TLP. The spec says you can optionally check that and report it as a malformed TLP, but you're not required to. So I'm not sure. It's up to how your chipset is configured or whatever. Now, if you're doing peer-to-peer DMA between two FPGAs, you could probably bend the rules if you wanted to. But I don't think it makes that big of a difference because we're just talking about a couple of additional TLPs on top of a 4K transfer. That's a relatively small overhead. Well, the other thing too is that in most cases you're not going to be able to issue a 4K transfer in the first place because the max read request size and max payload sizes are probably going to be set a lot smaller, right? So in your example of 3K, then you're going to be issuing probably a bunch of 512 byte reads or writes. So if you have to break it one of those on a 4K boundary, it's a pretty small overhead.
Yeah, exactly.
Thank you.
Alex.
Sure, what's up?
Oh, okay, you can read me, great.
Yeah.
With respect to the AXI DMA, I guess when you're issuing read requests, for example, to the PS DRAM, I would think that the completions could come in out of order. So they would preserve the IDs, but a DRAM controller may choose to respond in a different order.
How deep is the reordering? Is it just just a couple, or could you be getting one like 10 whole transfers later, right? It seems like you might have some reordering, but it's only going to be on the order of a handful of clock cycles, right? I could be mistaken about that, but I think the bigger reordering issue is going to be like if you're hitting multiple devices on the other side, and there's delays and whatnot between those. But if you're hitting the same memory interface, it seems like you're going to be getting less reordering. And the other thing too that I was scratching my head over is that if you're going to reorder in the memory controller at all, then you have to check the IDs, right? Because AXI, if you give it the same ID, then you're not allowed to reorder. So I guess there's a trade-off between, do you check the IDs and reorder and pay, an additional bit of logic for that, or do you just say we're going to preserve the order?
Well, I would say from a performance perspective, I guess you would have some benefit depending on your access pattern from using multiple IDs, because otherwise the memory controller can't optimize on your accesses, right? So it has to stick to the order you chose, without being able to see to look at the memory state. So which banks are open, which needs to be closed, and so on. So you have to wait for potentially for a refresh or whatever with all the accesses, despite just one of those in the row.
That's true. That's true. Yeah, I guess I'll need to take a look at the data sheet for that a little bit more closely.
Well,
I guess the other
if
thing
you just
too,
have a look at the PL MIG, then it already says something about it, which is definitely a different implementation, of course. It's another DRAM controller, but even the PL implementation does some reordering based on bank groups, I guess.
right. Well, I guess that's something that can be revisited. We can start with the kind of simple implementation that we have now, and if I have to, you know, implement a FIFO or something to properly handle the, you know, deeper reordering, then that can be done. It's just, you know, a question of, you know, logic resource consumption in the DMA engine.
Yes, yeah, of course. Yeah, I guess we are looking forward to getting access to the code, and I guess we are also happy to review it and also test it. So if you just I don't know, once you're happy with it,
maybe
to
I
open
can get
it
you guys a
and
copy of this earlier, so you guys can test it out in hardware and see if it actually works.
yeah, I guess that would be great. From my perspective, depends on how you like it. You could just open a branch and push it to the branch, and then we'll see. Or I don't know. We can also send back and forth tarballs or whatever is better for you.
Right. Yeah, I'll take a look at that. Yeah. So I guess my original thought is, you know, I was going to test it on hardware here, but you know, if you guys want to do that on your end and start using it sooner rather than later, then you know, I guess we can make that happen.
Okay, cool.
Yeah, I mean,
just think about
thing,
it and drop me an email or whatever, and then
yeah,
we can have another chat.
I could just zip these files up too, and then you know, if there's some obvious problem, that I can fix that before, you know, getting it committed. Because even if I commit it, it's going to be going. I mean, I was going to put this into the PCIe repository along with everything else. Although at some point I should probably rename it from the PCIe repository to, you know, the extensible DMA framework or something, because this is definitely growing to more than just PCIe stuff. I don't know. So yeah, I mean, at some point it'll definitely make its way into the, you know, main Corundum repository. But yeah. Oh, and speaking of PCIe stuff, I have been doing a little bit of work on the PCI Express code over the past few days, and I've updated the PCI Express AXI Lite master module to support arbitrary read and write operations. So previously it only supported single D word operations. So I made a copy of it, PCIe AXI Lite master minimal, that only supports the single D word operations. And then I have the you know, the main module now supports arbitrary operations. So as far as the main Corundum code for how that works, it's probably not going to make much difference because the driver doesn't take advantage of that. But I could definitely see that being useful for people working in the application section. If you want to be able to do even 64-bit reads and writes, you know, you need the updated code for that. And the other thing that I also got working is the AXI master modules are now ported to using the new DMA, or the new PCI Express interface setup. So that'll mean that I'll be able to put together some new example designs using all of the updated modules, in the process of doing that. And then also this will be used in the unified DMA address space setup in Corundum. So you can access you know, the on-card DRAM both through PCI Express and through the DMA infrastructure. So that's another piece where I'm going to be using these, you know, new AXI DMA interface modules. But yeah, getting all of those pieces working together is going to be a little ways down the road still. Anyway, does anyone else have any questions or comments or concerns or? No? All right. Well, oh,
if we're to add support to a device that you don't have access to, would you want us to submit a pull request, or should we just create a separate branch for that?
I mean, so the problem is that if I don't have access to the hardware, I can't maintain that interface code. So in terms of kind of the core logic, that's not really a major problem because, you know, the core logic doesn't really have anything board dependent. But in terms of, you know, all of the board dependent stuff, you know, I have no way of testing that. So as you'll notice, pretty recently, I totally rewrote all of the board level designs. So if I need to do something that touches all the board level designs, one of the changes that I'm thinking about potentially in the future implementing is adding a small RISC-V core to handle all of the, you know, board specific interfacing I2C and whatnot. You know, if I want to implement that, if I don't have the board, I can't test it. So I'm kind of leery about adding support for devices that I don't have access to because, you know, then I can't support, you know, the code running on that device. So yeah, I mean, you can port it to whatever devices that you want. If it's not something that I can also get my hands on pretty easily, then, you know, that's going to be an issue. So yeah, in terms of your alpha data boards, I've been looking here and there to see if I can get my hands on one, but I think they've been like discontinued or something. It seems like they maybe didn't even make very many of those to begin with. So
yeah, it seems like I got kind of lucky with the 2 I have, so it might be kind of hard to find an additional one.
Right, yeah. Those came off of eBay, I think you said.
Yeah, it was from some recycler.
I mean, that's where most of the stuff on eBay comes from, you know. Occasionally you get something that's not from a recycler, but the advantage of stuff coming from recyclers is they usually don't know what the value is of the stuff that they have. So they put some number on there, and if you know what to search for and they didn't do a completely terrible job of listing it, you can get really good deals.
Yeah, I've been trying to get some 9v3s, but the only people who ever seem to list them know what they are, so it's kind of been tricky.
Yeah, they are relatively nice boards. I mean, if you need something with larger logic resources, I would recommend, if you can find a way to cool them, the BCU 1525s. Those tend to come up for, you know, like around $1,500 or so, and they have a VU 9P, which is a really big FPGA. Flip side is they tend to be passively cooled, and if you're not installing them in a server, you need to find a way to get air moving through the cards. So they are more expensive, but they are much larger. Flip side is that if you have a faculty contact, you might be able to go through the Xilinx University program and, you know, get an Alveo board or something like that. So if that's something that you're interested in potentially doing, send me an email. I'll see if I can put you in contact with the appropriate people at Xilinx. Unfortunately, the request for that has to come from faculty or staff at the university. So you'll have to work with, you know, whoever your faculty advisor is to help make that happen. I think it should be doable. They've been pretty supportive of Corundum.
Yeah, I think it's a really neat project, and I think there's definitely a lot of applications that could be ported to Corundum that would be really helpful.
Yeah, I think so. The other thing I'm hoping is that some of the FPGA board manufacturers are going to be more supportive of Corundum and will actually, you know, either provide boards or, you know, help support it on their boards. Because just having a slot in the supported devices list for Corundum could definitely help move a few boards. But you know, I'm not privy to what goes on the sales side of some of these companies.
Yeah, I think that there's some really weird things going on as far as the pinouts and documentation regarding different interfaces, and it kind of gets really tricky from a lot of these vendors.
I mean, the thing with an FPGA is you can do pretty much whatever you want in terms of wiring things up. So everybody does something different, and then you have to, you know, make a slightly different design for every single board. What can you do? But yeah, the other thing that you get good at if you're buying boards off of eBay is reverse engineering them and figuring out what's hooked up to what. Anyway, anybody else have any other questions or comments?
Yeah, a little one.
Sure.
You mentioned the RISC-V addition.
Yeah.
For our internal, or at least IP product, yeah, demo designs kind of, or development designs, we are also looking at this. Do you have any list of recommendation or something to look at?
Well, so what I was thinking is we basically just need a really small kind of microcontroller type thing. It's not going to be running Linux or anything like that. It's just going to be, handling a few I2C operations and maybe a couple of other things. So the requirements that I had were basically it's got to run at whatever clock frequency PCIe is running at, right? Synchronous with the rest of the design. So it's got to be able to run at, 250 megahertz at least. But I don't really care about the performance, right? If it takes 10 clock cycles to, fetch an instruction, whatever, as long as it's running code. So I was probably looking at like the Pico RV32 core for that, because it's like one Verilog file, and it apparently can run at relatively high frequencies. I know some people have been, bad mouthing it because it's not a particularly high performance core, but I just need that high clock frequency. If the, instructions per clock figure is not good, whatever, because I don't need that. But if you're looking at something higher performance, Vex RISC-V is supposed to be really good and quite configurable. So I'm not
I
sure
guess
exactly
our
what your
criteria
application
are
is.
kind of the same.
Okay.
So
Okay.
we were
you want
also
something,
looking
you want
at,
something small, but not necessarily high performance, just for some
Yes.
housekeeping stuff. Yeah.
correct.
Yeah. Then
So we
Pico
were looking
RV.
also at Pico RV, the Palpissimo project, or the low risk, for example, because that's, I don't know, projects with more than one guy working on it, kind of.
True.
That helps to base your application on. Yeah, okay. Yeah, great. Thanks. I guess, yeah, maybe we share our last results of our research with you, and then maybe you have some additions on it.
Yeah, sure. Oh, somebody posted a Zoom. Okay. froze the Zoom tab. Oops. Yeah. Okay. Yeah, that happens occasionally. Yeah. Well, so yeah, we could definitely talk about that a little bit more, because I was thinking about adding a few additional pieces to Corundum to kind of facilitate working with that core, and potentially a utility to help load code onto the core or whatever to make debugging a little bit easier. So you could definitely do burn and turn on the FPGA to change the firmware, but that can get old if it takes a couple hours to build the design if you're just changing the RISC-V firmware. So but yeah, I also have yet to figure out exactly what all the interfaces are going to look like. Another example, or another advantage potentially of the Pico RV32 is that they have an AXI Lite wrapper, which could make it a lot easier to interconnect that with an existing kind of AXI Lite setup. I'm not sure what kind of interfaces you guys are using at the moment. I'm assuming most of the Xilinx standard ones, AXI Lite, but that is a
Yes.
consideration.
Exactly. So we were also just considering a course or infrastructure around the course, bringing a core with it, like a ZOC generator, for example, that incorporates AXI Lite interfaces. And actually, you don't have to recompile the bit file. You can just swap out the VRAM content.
Oh, right.
If you
Yeah,
change
that's
the
true.
firyw.
That's true. I mean,
at least if you don't enlarge the size of the code.
Well, too much. If you enlarge it a little, you're probably okay. But if you have to start adding more block RAMs, then you got a problem.
Exactly.
Right. Yeah. All right. Well, I guess we can discuss that too at some point. Hopefully sooner rather than later, but we'll see. It's so kind of my reasoning for including that core is just to remove all the board dependent stuff from the Corundum device driver, because right now it works fine, but it would make maintenance a lot easier if we didn't have that in there. And it also means that if you have like a DPDK driver in addition to a kernel device driver, then you'd have to synchronize board specific stuff over there. And then also if if potentially something gets upstreamed into DPDK or Linux kernel or whatever, then, having that device dependent stuff, centralized and located in the board just makes things a lot easier. So there isn't a particular reason to get that operational sooner rather than later, except for the boards that we're using at UCSD in one of the test beds. The Alpha Data ADM 9v3, ADM PCI 9v3 boards, and the way the I2C is set up on there, you have to use a separate select pin to select which module you want to talk to. And I've been trying to make that work using the Linux kernel I2C subsystem, but you have to pull in like a platform device driver to flip that pin, and then it's creating all sorts of module lock issues. So I can't reload the module very easily without jumping through a bunch of hoops. So I may end up looking into that sooner just to try to remove some of this stuff from the Linux kernel driver and make things work a little bit more reliably. Oh yeah, another thing that I just ran into a couple of days ago is I tried to build the driver on my workstation PC, which I recently updated, and it didn't build because they changed something in the I2C subsystem, and I had to, change the code in the driver so it would compile. So yeah, the less dependencies I have in Linux kernel, the better. I think from a maintenance perspective. So yeah, it's one of these things. I don't have time to devote to figuring it out. Like, I would rather work on other stuff, but if I have to sit down and, make that work just for my own sanity, then yeah. So potentially in the next few weeks, I'll take a look at that in greater detail and actually try to get something working, but I'm not going to make any promises at this point. Anyway, enough of my rambling. We're definitely over time at this point. If we get any more questions or comments from other folks, then that would be great. Otherwise, we should probably wrap this up. Anybody else have any questions or comments? No? All right. Well, thanks to everyone for tuning in. This has been a pretty good meeting.
Thank you, Alex.
Thank you.
All right. See ya.
Great. Thanks. Bye.
Thanks, Alex.
Thanks. Have a good 2 weeks.
Yeah, see you guys in 2 weeks.